Hi everyone. Welcome to week 1 of this 18-week Artificial Intelligence Fundamentals and Applications program with AI. In this program we will understand what artificial intelligence is and learn how to develop AI-based solutions to various problems. Before moving on to artificial intelligence, we will understand the artificial brain, how it can be trained and how it learns. Artificial intelligence refers to the development of computer systems and software that can perform tasks typically requiring human intelligence, such as problem-solving, decision-making, and learning. The concept of the artificial neural network, how it is trained and how it learns, has a close analogy with its biological counterpart, or the biological brain. Biological neuron. Here, you see a biological neuron. The human brain has approximately 83 billion biological neurons. Neurons are interconnected, constantly processing and sharing information. 5 senses. Information to the brain comes from the 5 senses humans have. They are: eyes for vision, ears for hearing or audition, nose for smell, tongue for taste, skin for haptics or touch, as well as temperature and humidity, etc. These information are the inputs to the brain. Brain processes the information and makes decisions and recommends actions. These decisions are the outputs. For example, you see your teacher. Your brain receives an image of your teacher. This image is the input information to the brain. The brain processes the image information, recognizes your teacher, and decides to say, "Good morning, teacher." This decision to say good morning to your teacher is the output. Neurons are the information processing elements of the brain. Architecture of a biological neuron. Let us take a close look at the architecture of a biological neuron. Dendrites. Dendrites receive the input from the senses directly or from the other neurons. Nucleus. Nucleus is the control center of the neuron, which processes the input information and produces an output. Axon. The axon communicates the output to the other neurons. Synapses. Synapses represent the connection strength between the neurons. When you learn something new, this connection strength can get stronger or weaker. It is a bit like when you practice a game, and you get better over time. Neural network. A collection of a large number of interconnected neurons is called a neural network. Artificial neural networks used in AI are computational models, inspired by the structure and function of the human brain. Artificial neural networks are used in machine learning and deep learning to process and analyze complex data, learning patterns, and making predictions by adjusting the connection strengths between neurons through a process known as training. So, before moving on to artificial neural networks, let us take a look at biological neural networks. A network of large number of neurons is called a neural network. Different parts of the brain have different sets of neural networks. These neural networks are responsible for different functions. For example, the neural networks in the optical lobe of the brain specialized in processing visual information. It is these neural networks that helped you identify your teacher. The neural networks in the frontal lobe specialized in planning actions and making decisions. It is these neural networks that decided to say, "Good morning, teacher." There are many more. Neurons operations. Now let us look at an animated video to better understand the neurons operations. Neurons talk to each other using both electrical and chemical signals. Messages start as electrical signals, traveling rapidly down a neuron. These signals are called action potentials. When they reach the gap between two neurons, the messages need some help to get across. The information is transformed from an action potential into a chemical message which crosses the gap called a synapse. The release of those chemical messengers can trigger an action potential in the neuron on the other side of the synapse, conveying the message onward. Or it can quiet the message. This happens over and over and over. And with repeated activity, the synapse gets stronger. So, the next message is more likely to get through. That way, neurons learn to pass on important messages and ignore the rest. This is how our brains learn and adapt to an ever-changing world. Artificial brain. Now, we know about the biological neurons, their interconnections and communication in the biological neural network, as well as the learning process in a biological brain. An artificial brain in artificial intelligence is a collection of artificial neural networks. It tries to mimic the biological brain. People started to think about how to make machines intelligent, not in the recent past, but in the 1950s. The artificial intelligence was a major topic at the Dartmouth conference held in 1956. An intelligent machine needs an artificial brain. As a result, over the years, mathematical models of neurons and neural networks were developed, so that an artificial brain can be implemented on a digital computer. Therefore, an artificial brain is a mathematical model of neural networks implemented in a digital computer. Mathematical model neuron. Here, we see a biological neuron that receives information or inputs from 3 other neurons. Now, let us take a look at the artificial neuron, or the mathematical model of neuron. X1, X2, X3 represent the inputs receiving from the other neurons. These are simply called the inputs. W1, W2, W3 represent the connection strengths between the neuron and the other neurons. These are called the connecting weights. Y represents the output of the neuron. F is the function that describes the relationship between the input's output and the connecting weights. The function F is called the activation function. Activation function. This example shows how to use the activation function to determine the output using the inputs and the weights. For simplicity, here we consider a linear activation function. In the function, the B is a constant. It is called the bias. Now let's do an exercise to determine the output of a neuron. Artificial neural network. A network of artificial neurons is called an artificial neural network, or ANN. A neural network can have many inputs and many outputs. Input layer neurons receive information or inputs from outside. It can be from the sensors or from other neural networks. Output layer neurons produces the final output. In between the input layer and the output layer, there are one or many other layers of neurons. They are called hidden layers. The connection strengths of the different layers are represented by connection weights. Large neural network has large number of weights. Now let us do an exercise to determine the outputs of a neural network. Now, we know about the biological neurons, their interconnections and communication in the biological neural network, as well as the learning process in a biological brain. The concept of training and learning. Having understood what an artificial brain is, it is now time to understand how it can be trained and how it learns. Let us first understand what is meant by training and learning, as well as the concept supervised and unsupervised learning, as well as reinforcement learning popular in artificial intelligence. What is training? Think about going to a driving school to learn how to drive a car. In driving a car, what you see are the inputs to your brain. Your driving actions, such as steering, accelerating, and braking, are the outputs. In the driving school, you get a trainer or driving instructor to train you how to drive. Actually, your brain is trained how to drive. We can explain this whole training process as follows. Based on what you see, the inputs, you generate driving actions, or the outputs. Your trainer observes your driving actions, or the outputs, and gives you step-by-step instructions how to correct or improve those driving actions. Your trainer trains your brain, and your brain learns how to drive safely and efficiently. The inputs and the trainer recommended outputs are the training information, or training data, your brain uses in this training process. Similarly, training an artificial neural network requires training data. After the training period is over, you will take the driving license test. Also, in artificial intelligence, the trained network is tested, using test data to test whether the training is successful. This is called supervised learning. Reinforcement learning. Reinforcement learning is another method that is heavily used in modern-day artificial intelligence. Now, imagine you are in a driving school again. But this time, your driving instructor is not giving you step-by-step instructions. Every time you make a turn, accelerate, or brake, your instructor gives you a reward if you did something right, or a penalty if you made a mistake. You use this experience to produce actions that lead to higher rewards, and avoid actions that result in penalties. In artificial intelligence, reinforcement learning is similar. The neural networks produce actions and receives rewards or penalties based on those actions. Over time, it learns to take actions that lead to higher rewards and avoid actions that result in penalties. Learning can also take place in unsupervised way or without a trainer. Now, let us say you are exploring a new area with your car. But this time, without a trainer. You are not getting any guidance. As you explore, you start to notice patterns in the traffic, roads, and pedestrians. You might notice that certain types of traffic tend to be in specific areas, or that some roads are busier than others. Here, you are learning about the world without anyone telling you what's what. This process of discovering patterns and grouping similar things together is similar to how unsupervised learning works in artificial intelligence. The neural network looks at a lot of data and tries to find patterns or similarities without any explicit instructions. Training process. Now, let us discuss the supervised training process, in an artificial neural network. Supervised training requires input training data, as well as output training data or the desired outputs. In here, the input layer of the neural network receives input training data. For each input training dataset, the neural network produces an output. Let us call this the actual output. This output is compared with the desired output from the training data. The difference between the desired and the actual outputs is the error. The connecting weights are adapted in a way this error is minimized. This means an artificial brain learns how to produce the correct output by adapting its connecting weights. Let us take a look at a practical problem that can be solved using a simple neural network. When connected to a load, such as a light bulb, a battery produces DC current. The value of the current depends on the load. This means different loads draw different currents. Batteries have an internal resistance. When there is a current, battery terminal voltage drops due to this internal resistance. Here you see the electrical circuit diagram, where IC is the circuit current, VT is the battery terminal voltage, R is the internal resistance that we assume to be constant, E is the open circuit voltage or the terminal voltage when there is no load connected or when the current is zero. For a healthy battery, this is constant. The circuit equation can be written using the Kirchhoff's voltage law as VT is equals to negative R multiplied by IC plus E. According to this equation, terminal voltage drops with increasing current. Determination of battery internal resistance. We will study how AI can be used to determine the internal resistance of the battery experimentally. In the experiment, we vary the load to vary the circuit current. We record the terminal voltage at different values of the circuit current. The experimental data is shown in the table. This data will be used to train the neural network that we will see shortly. Take a look at the circuit equation. Here, R and E are constants. IC and VT are variables. Circuit equation takes the form of a straight line, or Y is equal to mx plus c. If we use the collected experimental data to find the equation of the straight line, we will know m. Then the internal resistance, R, can be found as R is equal to negative m. The neural network and training. Here, we will study how to get a neural network to learn the relationship between the circuit current and the terminal voltage using the experimental data. In other words, to find the equation of the straight line that best fits the experimental data. This is called curve fitting or regression. Circuit current is the input to the neural network. Hence we need only one neuron in the input layer. Terminal voltage is the output of the neural network. Hence we only need one neuron in the output layer. We only require just one neuron, also in the hidden layer, to realize our linear regression task. W1 and W2 are the connecting weights. B is the bias. VT, or the output of the neural network, can be obtained by multiplying the output of the hidden neuron by the connecting weight, W2. When rearranged, the equation of the neural network takes the form of a straight line. Y is equals to mx plus c. That means this neural network can learn the relationship between the circuit current and the terminal voltage. The blue dots shows the experimental data we collected. Horizontal axis is the circuit current, and the vertical axis is the terminal voltage. We use this data to train the neural network. We usually call them the training data. We want the neural network to learn the straight line, or linear relationship between the terminal voltage and the circuit current. The red color line is the straight line produced by the neural network. You can clearly see the learning process. The line fits the data better with each training cycle. In AI literature, a training cycle is called an iteration or an epoch. You can also see the equation of the line and how it changes in the learning process. Initially, the neural network output has an error. This error reduces or comes down when it learns better and better. We will discuss this in the next slide. The error function. Let us try to understand the training and learning process. In the table, we have the data collected from the experiment. Equation of the neural network is also shown here. Let us consider the first training data pair, IC is equals to 0. VT is equals to 9. When substituted in the equation of the neural network, we get the output of the neural network as BW2. Now compare the output from the training data and the output of the neural network. The difference is the error. Therefore, we have that error equals to 9 minus BW2. Next, let us consider the second training data pair. IC is equals to 1 and VT equals to 8.7. Whence, substituted in the equation of the neural network, we get the output of the neural network as W1 W2 plus BW2. Now, by comparing the output from the training data and the output of the neural network, we have that error equals to 8.7 subtract by W1 W2 plus BW2. Likewise, error corresponding to the third data pair is shown here. Error corresponding to the last data pair is shown here. Now, we have the neural network output error related to the first training data pair, second training data pair, third, and all the way to the last training data pair in a complete training cycle. The total error in a complete training cycle, or an iteration, may be taken as the sum of the squares of all these error values, as shown here. Neural networks learn by adapting its weights. As we can see, the total error, given by the error function, depends on the connecting weights, W1, W2, and the bias, B. This total error can be minimized by adapting the connecting weights and bias. This is exactly what happens in the training and learning process of the neural network. In summary, output of a neural network depends on its connecting weights. Hence, the accuracy and error of the output depends on the weights. In the training process, the neural network adapts its weights to learn to produce accurate outputs. Let's try to understand the weight adaptation process. Weights after the first, 20th, and 40th iterations are given in this table. Now open the calculator in your computer, substitute these values in the error function, calculate the error, and fill in the table. You will clearly see how the weights are adapting, and the neural network output error is reducing when the training and learning process progresses. Adapting the weights in a way, the error function is minimized is called optimization. There are several ways to achieve this. One of the simplest methods is random search. In random search, the weights are randomly selected and substituted in the error function. The weights that produce the minimum value for the error function is chosen as the optimum weights. This is optimization. If you have already studied differential calculus, you know that the minimum of a function, fx, can be found using the derivatives, or the gradients. Gradient-based methods are also widely used as an optimization method in AI. There are many other methods. If we use Python libraries, we can select the optimization method by selecting one of the many optimizers that Python offers. You will use some of them in the coming weeks. For instance, in Week 5, character recognition neural networks, we will use Atom Optimizer that uses a combination of two gradient-based methods. Let's get back to the practical problem we are trying to solve. That is, finding the internal impedance of the battery using the experimental data. We got the assistance of AI to find the best fit straight line for the data as Vt equals to negative 0.194 IC plus 8.879. And the circuit equation is Vt is equals to negative R multiplied by IC plus E. By comparing the two equations, we get R is equals to 0.194. Therefore, the internal impedance of the battery is 0.194 ohms. Solving complex problems using AI. As we just witnessed, simpler problems, such as finding the internal resistance of a battery using circuit current and the battery terminal voltage, may be solved using a simple neural network having a single neuron in the input, hidden, and the output layers. What we see on the screen are handwritten number characters. Artificial intelligence can be trained to successfully recognize handwritten characters. Complex problems require complex networks. Relatively much complex tasks such as handwritten character recognition may require 784 neurons in the input layer, multiple hidden layers, and 10 neurons at the output layer. In Week 5 of this program, you will in detail learn and test handwritten character recognition using a single neural network as well as using the deep network and deep learning.